Hi, this is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to take you through ear simulators and how they're used in Ares. If you think there's some material that I didn't cover, or you have questions, or you think something is wrong with how I'm handling them, please feel free to contact me. You can use the May email address that's found on the May website, or you can follow this video to YouTube where it's posted, and you can make a comment underneath the video. But I'd like to hear from you. Okay, so I'm going to start out with what is an ear simulator. From my perspective, there's two main purposes of an ear simulator. It's to provide a consistent and known acoustic load to your acoustic device or acoustic circuit, and it's to provide an estimate of the DRP or drum reference point pressure that your ear is sensing. DRP is generally thought of as the eardrum pressure, but I'm not entirely sure that that's accurate, but it's referred to DRP nonetheless. So there are 2 points referred to with these ear simulators. There's ERP, which is the ear reference point. This is meant to be a fictitious plane at the entrance of your pinna, where they're going to measure sound just at the surface of your ear. And then there's the DRP, or drum reference point, which is meant to represent a point just in front of your eardrum. Now this is a mechanical simulator. It's the sealed ITU Type 1 simulator. And the idea is that this simulator is going to generate a voltage out of its internal microphone, which is proportional to the eardrum pressure. So the actual DRP pressure is equal to the voltage out of the simulator, microphone voltage out of the simulator, times some kind of a calibration constant in units of pascals per volts, where this cal constant is just a simple scalar number. It's not frequency dependent. Here's a list of documents that are good to review if you want to understand these artificial ears or ear simulators a little better. There's some ITU specs. The B&K data sheets are excellent, and here's some IEEE specs that are worth looking at. Almost all of the information that I use to generate the ear simulator data in Ares has come from these documents. Okay, so ear simulator use in Ares. This is the icon for the ear simulator. It's got 3 nodes that you can connect to. This red node is the ERP point. This is the node that you connect your acoustic circuit to properly load it down with the impedance of the ear simulator. The DRP point on the right here is a blue node. The blue nodes are referred to as listening nodes. The pressure at these nodes is just a simple transfer function from the pressure at the ERP node. So you can't load this circuit down at all. Even if you put a very, very small load on here where it has to drive a lot of volume velocity, the acoustic simulator will put out whatever drive velocity it needs to create that the pressure, which is just a transfer function from ERP. So the blue nodes are just nodes that you attach a graph element to listen to see what the pressure response is like. Now there are 2 types of ear simulators generally in use. There are mechanical ear simulators and then pinna-based ear simulators. The mechanical simulator is what we've already seen, the ITU Type 1. It doesn't look much like an ear, but it does give very repeatable data. But you have to be careful because you can get kind of some non-physical effects from it. The pinna-based simulators, they're more realistic, both in terms of what they look like and in how they mechanically interact with a device that you might place up to an ear. The data is a little bit more representable of actual use because you will have the effects of the pinna, and if the pinna is attached to a head and torso simulator, you will get the shadowing effects of the head. But it's much harder to get more repeatable results as the position of the device on the ear and the force used to deform the pinna have to be repeatable. There is a third node on the ear simulator in Ares that I forgot to mention, and that is for the diffuse field response. I'll cover that a little bit more later, but this is meant to be the pressure in a diffuse field which would generate the same DRP pressure as produced by your acoustical circuit. I'll cover that in more detail though. So as I mentioned, mechanical simulators don't always give realistic physical responses. Here's the B&K 4185 sealed simulator, or it's the ITU Type 1 simulator. Here's a phone that's had its earpiece puttied to the sealed simulator, and its response is being measured. Now, for this particular phone, the diameter, the sensing diameter of this ear simulator is 1 inch. That's largely meant to match the size of the concha bowl. But if you cut a 1 inch hole out over the earpiece area of a phone, that 1 inch diameter may not fit your ports perfectly well. So if you've got a port that's outside of that 1 inch, it's not going to be captured in this ear simulator. This is an older phone. On newer phones where the earpiece is moved right up along the edge, you have the problem of not having any surface to mount the ear simulator to. Maybe if you just mounted it to that very edge and puttied it in, it would be a more representative sealed condition. But a phone like this probably wouldn't be used with the sealed simulator anyway. There are low and high leak simulators that would probably be appropriate though, but with them you've still got the 1 inch diameter issue in interfacing that to your product. So an example of how the ear simulator would be used in a circuit. Here's a Sonian receiver is being used with its typical hearing aid tubing down to an ear simulator. It's connected to the ERP node for proper loading, and the graph is connected to the diffuse field listening point to get an idea of what its response would be like in terms of listening to this device, listening to the audio generated by this device in an equivalent diffuse field environment. What the Ares simulator does is it presents the correct impedance into the ear simulator at the red node. The ERP pressure will also be present at that red node, and then Ares applies an ERP to DRP transfer function to compute the pressure at the DRP node. It then applies another transfer function to translate the DRP pressure into a diffuse field pressure. This transfer function is taken from the ITU P.58 specification, whereas the ERP to DRP transfer function is dependent upon the simulator. So as an exercise, I'm going to open up Ares and show you how you can plot this ERP to DRP correction term. So here's Ares. To do that, I'm going to create a modeler module. I'm going to create a pressure source. I'm going to create an ear simulator, and I'm going to go ahead and connect the pressure up to the ear simulator. Now, to keep things normalized around 0 dB, I'm going to set the pressure to 0 here. I'm going to go ahead and create a graph element, connect that up to DRP, and hit calculate. So here's the graph that was created. And I'm going to make the line weight a little heavier to make it easier to see with the video. And this is the DRP correction curve for the default ear simulator, which is the ITU Type 1 or 4185, B&K 4185 ear simulator. Now the ERP to DRP correction data from the B&K datasheet only goes up to 8 kilohertz. So after 8 kilohertz, the correction just takes on the last value and it becomes flat. This isn't physically reasonable, but that's as far as the data for the simulator goes. You could possibly extend it, but really the equivalent circuit assumption behind these simulators really breaks down up here, and there's not a lot of physical reasoning to extend it. To see this curve for the other simulators, namely we'll look at the low and high leak and the IEC 711, we can select these four for iteration and then iterate on the simulator. Go ahead and bring that curve up, and now we see the ERP to DRP correction curve for the four main simulators used in Ares. These peaks are generally caused from resonances in the ear simulators that are meant to largely capture the resonant behavior of the ear canal tube and to some extent the radiation loading of the sound that's escaping from around the pinna. So you'll notice that the sealed simulator in red here and the IEC 711, which is meant to simulate just an ear canal, they're both pretty flat, but they have an ear canal resonance up around 5-6 kilohertz or so. The 4195 low and high leak simulators have that same resonance. It's shifted down slightly in frequency. And then it has a second resonance around 3 kilohertz that's largely caused by this leak around the pinna. The sealed simulators don't have that leak, and so they don't have this second resonant peak in their response. I'm also going to take this time to look at the impedance into these ear simulators. So I'm going to create a new graph element, hook it up to the ERP point where the impedance is meaningful. I'm going to select impedance in the graphs options, and I'm going to go to advanced options and have it plot real and imaginary. This is the data. This is the graph that element created. I'm going to go back and change the line weight to 3 again to make it more visible for this video. Now I'm plotting the magnitude of the impedance in the top graph and the real and imaginary parts below. I'm going to temporarily focus on the just the 4185 sealed simulator right now. So I'm going to hit calculate and get rid of the iteration data. So this is what the impedance looks like for the sealed simulator. I'm going to extend the low frequencies a little bit here. So I'm going to go into the global parameters and go down to all the way down to 10 hertz with this. Hit calculate. No, it didn't bring it up. What'd I do? 10 hertz, calculate. Bring graph to top. Yeah, there we are, down to 10 hertz. So I wanted to bring this up because the low frequency impedance into the simulator is looking like a sealed volume. Here's the imaginary part with the dashed line. It's following a negative J over omega curve, which means it's a sealed simulator. It's a sealed volume at very low frequencies. And then its behavior gets very small at high frequencies, mostly because that the impedance into that volume gets tiny as omega gets large. And then you'll see the resonant peak in the impedance of the simulator and various other behaviors going on. But if you want to understand whether the load is behaving like a real resistance applying a lot of damping, or whether it's a capacitive load with a negative imaginary part, or whether it's an inductive load with a positive imaginary part, it's good to look at the real and imaginary parts. But to get an overall idea of what the impedance is like, the magnitude in dB is very useful. So I'm going to go ahead and uh, turn off the real and imaginary part. I'm going to reiterate on the simulator so we can look at the magnitude of impedance for all these simulators. That's shown here now. So it's good to be able to understand why the simulator has the impedance it does. Right away, here's our ear. The red curve is our sealed simulator. This is meant to represent the condition when a large phone, an old-fashioned landline phone, is held to the pinna and it creates a largely sealed condition around the pinna. It may seem inconceivable that you could possibly seal to the pinna due to its folds and crevices and whatnot, but I have had a phone that didn't have an internal leak structure associated with it that I would use, and it would commonly get stuck to my ear and I'd actually have to pop it off. So the sealed simulator is realistic for large landline type phones. Notice that because it's sealed, it has a very large impedance at low frequencies. You should try to get used to understanding what impedance looks like in terms of dB acoustic ohms. So this simulator in the mid-band up here around 1 kilohertz is in the 140 dB range. At low frequencies, down at 20 hertz, it's up around 160 dB. So that's an increase in 20 dB or a factor of 10 in its impedance at low frequencies. The low and high leak simulator are meant to capture when you hold a phone to your ear and there is a leak associated with not sealing to your pinna. For instance, the newer cell phones would be examples of why you'd have a leaky condition because the phones have their earpieces close to the edges and they can't seal as well. So this gold colored curve here is the low leak simulator. It has similar impedance behavior around 1 kilohertz, but at low frequencies, because it's leaking, it has a much lower impedance than the sealed simulator. We're below 130 dB here. And then with the high leak simulator, it's another 15, almost 20 dB below that. So there's the impedance at low frequencies is very small, and it's hard to drive these low frequency impedances. You need a lot of airflow to create a decent pressure down there. So because you have such a large variation in impedance, you'll get a large variation in the pressure response from these simulators. Then at high frequencies, you can see the resonance effects, which will also affect the sound generated from the simulators. All of them have this ear canal resonance between 3 and 6 kilohertz, and then the sealed low and high leak have some additional resonance behavior. But this is the load that you're driving to try to create a pressure response to the user's ear. Now these are the impedance functions that are in the standards, but real ears will have quite a bit of variation. If you design your products for these impedances, you can spend a lot of time perfecting it, getting it to be perfect for these impedances, maybe within a few dB, but you have to understand that you're going to have a lot of variation when it comes to that device being put up to a person's ear. This slide is taken from the ITU P57 specification, and it shows the impedance data that was used across many users for creating the ear simulators, in this case the sealed low and high leak simulators. Notice that the impedance seen varies quite a bit. There's almost a 20 dB variation over most of the frequencies, and there's even a 40 dB variation at the lowest frequencies. 20 dB is a factor of 10. That's a lot. 40 dB is a factor of 100. That's huge. So if you spend a lot of your time perfecting your design for the average impedance load, that's all well and good, but understand that your actual use case will have quite a bit more variation. Now this was impedance placed up to a pinna. When you're designing for an ear insert, which will use the IEC 711 coupler, this variance will tighten up quite a bit, but you'll still have probably at least a 6 dB, 10 dB window of variance for users there, and the actual resonances will shift around a fair amount as well. So I just say this to caution you in spending too much time trying to perfect your design into these ear simulators. Ultimately, you're concerned with what the user experiences, which is going to have a lot more variation than what you're going to expect if you just pay attention to the results of these ear simulators. Probably the best way of finding out what an actual user is hearing is to use an ear canal microphone. Etymotic sells a very nice one, and you can actually measure the response in several people if you want to see what the actual DRP response is looking like. So this is just a word of caution about trying to perfect your design a little too much. So I initially mentioned that there's mechanical and pinna-based simulators. Here's all of the mechanical simulators that I'm aware of. I'm actually missing one. How do you pronounce it? Zokowski coupler. It's an old one that was issued before the ITU Type 1. But this is the ITU Type 1. The B&K part number for it is 4185. This is used to represent a sealed condition to a phone. It was recognized early on that there's an issue with leaks. So at one time an adapter was made for this that would provide a consistent sealed leak. I'm sorry, a consistent leak for the phone interface using something called the German leak ring. This was, I don't believe this is in use anymore, but you might find some references to it. The low and high leak simulators are shown here. These are referred to as type 3.2, but there's two variants of it. A low leak simulator here has a very small leak around the perimeter. It's just a small slot. And the high leak version has a whole bunch of holes drilled into it. And then finally, there's the ITU Type 2, or what's commonly referred to as the IEC 711 simulator. This is just to capture the ear canal. So this isn't expected to include the pinna or concha bowl at all. It's just the impedance into an ear canal. One of the important things about these ITUs is that these are what's used, as far as I know, in all of the pinna-based simulators, and you'll see that a little later on. These are also commonly used for ear insert testing and hearing aid testing. So it's recognized that how you hold a phone to your ear will vary. You can press it firmly and have a sealed condition, or you might hold it loosely and have a low leak condition, or it may not be pressed against your pinna well at all and you might have a high leak condition. How the sealing to your pinna varies will affect the sound that the user hears. So in this next part, I'm going to talk about the notion of a leak tolerant design. That is, you'll want to try to design your earpiece so that it has a fairly uniform response under all of these three conditions: sealed, low leak, and high leak. So I'm going to bring Ares back up, and I'm going to create a new module, modeler module. I'm going to put together a simple circuit here. Hook this up. So we have a simple speaker with a rear volume that's directly driving the ear simulator. Now I'm not going to try to design this at all. I'm just going to take the default values for all of these and just hit calculate. I'm going to create a graph element, and I'm going to look at the diffuse field response. Here's the graph that was created again. I'm going to go and change that line weight again. And here's the response we're getting out of it. Not great, but we're not really trying to design it. It's a sealed simulator, so we get a lot of low frequency bass out of it. That internal volume attenuates the sound quite rapidly above 1 kilohertz. So this would be very boomy, not very much high frequencies out of it at all. Not a great design. But how well does this work as we change the load? What's its leak tolerant behavior look like? To look at that, you can go to the ear simulator. These check marks select which one you're going to iterate on. So I'm going to iterate on the sealed low and high leak simulators. Hit the iterate button, bring the graph up, and here is its response for those 3 simulators down to 100 hertz. So at higher frequencies, they're kind of close together, so you might expect the high frequency behavior of this earpiece to be fairly consistent, but how much lows the user hears will vary a lot depending upon how they seal it to their pinna. So you can expect a lot of low frequency variation, and the high frequencies are a little bit better. But regardless, this isn't great. You don't have a flat response anyway, so you wouldn't use this. In general, when you design earpieces, you attenuate the sound down to a certain level. So we'd probably try to equalize all this down to maybe 110 dB by putting in various structures to leak this sound away in a controlled fashion, and then probably add some kind of a resonator to try to add some boost up around 3 to 4 kilohertz, and that would be your earpiece design. Ares has a feature to make this leak tolerant design effort a little easier. You can go to the graph element, go to advanced options, and there's a option here to plot leak tolerance. Ares automatically looks at your iteration values and sees if you iterated with these 3 simulators. If you did, it will create another plot where it plots the difference between the sealed simulator and the low and high leak simulators. So ideally you want this difference to be 0 dB. You want them to be identical so that the sound that the user hears doesn't change as their coupling to their pinna changes. So this graph kind of becomes a metric of how well you're doing in achieving a leak tolerant design. And you might want to use the new cursor feature to help you evaluate this. You can right-click on a graph, select New Cursor, and when you drag it around, it reports the location of the cursor, and you can drag it to different curves. But you can double-click on this and tell it, I want to do some curve fitting, and I want to see the average value. It creates these bars that you can drag around, and now it's computing the average value over this range as 1.9 dB, almost 2 dB of variation with what is this? With the low leak simulator. Over that same range, the high leak simulator has an average variance of over 3 dB. You can expand that to whatever you want. But in general, you want to try to create a design that has a good leak tolerance. You do that by adding various port and volumes to this. I'm not going to cover that in here, but leak tolerance is an important topic with ear simulators. Okay, so that was that demo. Real pinna simulators. These usually go along with head and torso simulators because you capture the diffraction around the head and reflections from the torso. There's usually a realistic pinna made out of a low durometer rubbery or silicone material. This is the simulator from B&K. This is the hat simulator from Head Acoustics. I believe they do have a realistic pinna now, but originally they designed a greatly simplified pinna. They felt like they had some kind of market need for that, and that became part of the ITU specification, and that's the 3.4 pinna. This is the 3.3 pinna. There is one other common head and torso simulator used. This is called KEMAR. It's currently offered by Grass. It was originally developed by Knowles for hearing aid type work, and so it just largely existed in that market. But Grass has acquired the KEMAR from Knowles, and they've made some very nice advances to it, which may even make it more applicable than the B&K head and torso simulator. I'm told that the ear canal design is more realistic in their soft pinnas than what's found in the B&K simulator. I mentioned that the ITU Type 2 or IEC 711 simulator is what's used in all of these head and torso simulators. So here's a B&K artificial ear with the pinna in place. You can just see that there's a microphone on the other side of that short simulated ear canal. Here, the pinna has been removed, and you can see the 711 clearly. So keep in mind that this simulator, again, is meant to simulate the entire ear canal, so that little short ear canal isn't terribly important. You're still capturing the correct acoustical impedance load. But this rubber pinna may not be the best for putting hearing aids and ear inserts into, because it's so short and you hit the 711 right away. I believe that's where the new KEMAR has a little bit of advantage, that they designed a better ear canal with a soft pinna than what you see with the B&K hats, but I'm not 100% sure on that. So I mentioned that the ear simulator has that diffuse field node on it. So I'm going to talk about free field and diffuse field responses with head and torso simulators with hats. The mechanical simulators just measure a very local pressure when you put the phone directly up to the ear, but all of these sound pressures that you're trying to create should really be referenced to a natural listening condition, which is either going to be a free field or diffuse field condition. So the free field response, what it does is you create a sound field with just plain waves. You put a free field pressure microphone in that field and measure the pressure with nothing present. You then place the hats in that same field, and you measure the response from the DRP response from the ear simulator's microphone. The transfer function then of the hats response, the DRP hats response, divided by the free field pressure with just the microphone, becomes the free field hats response for that hats. So it's understood that even if you have a flat sound field here across all frequencies, this DRP pressure won't be flat. It's going to include the ear canal resonance and other things. So if you want a flat response from your device, you really want to try to recreate the spectrum that you see on the DRP mic when you place a hats in a free field condition where the free field pressure is flat. Free field is commonly used for talkers because you're expecting the talker to be directly in front of the user. Things are a little different when you're in a diffuse field where the sound can be coming from all directions. This is more of a music type application. You do the same procedure. You have a diffuse field with a pressure response. You put the hats at the same location of the microphone, and you measure the response of the DRP response from the hats. You divide the two, and you end up with a diffuse field hats response. And there's a slight variation between diffuse field and free field. This graph here shows those two curves. It's been normalized to 0 dB at low frequencies, and you get a rise of between 15 and 18 dB in the response of the hat's artificial ear due to the ear canal resonance, and you get some slight other behavior at the higher frequencies. The main difference between these two is the diffraction around the head and reflections from the torso. But this is not flat. Again, if you're designing a headphone, you don't want a flat DRP response. You want a DRP response that mimics these diffuse or free field responses. The diffuse field node on the ear simulator applies the inverse of this blue diffuse field response to the DRP pressure so that it will show you what the equivalent diffuse field pressure would be to produce the same DRP response out of the simulator. I know that's kind of complicated, but on the video you can go back and replay that and hopefully it makes sense. To see what these different responses would look like for a simple ear insert receiver, I've got them plotted here. This is a Sonian receiver with hearing aid tubing attached to the ear simulator. The IC711 simulator is being used in this case, which would be appropriate for an ear insert headset. The ERP result is shown in blue. DRP is in green. It's slightly raised due to the resonant conditions. And then when you apply that diffuse field correction to the green curve, it drops down quite a bit. So in my mind, it seems that Sonian is designing these receivers to be flat for a DRP response, but they're not very flat for the diffuse field correction, which doesn't seem optimal to me. But I've heard that with ear inserts, most people want a more boomier sound out of them. I'm not entirely sure why. I don't design these things, and I'm sure everyone has their own opinion. But the modeler is providing you with the ability to see that. So what should you design to? ERP, DRP, diffuse field, or flat, or free field? Which one should be flat? In general, my best understanding is you don't want to design to a flat ERP. You don't want to design to a flat DRP. You do want to design to a flat diffuse field response, particularly if you're designing it for music. And you would want to design for a flat free field response if your main focus is speech, with someone talking directly in front of you, and they're going to create more of a plane wave as the wave strikes the front of your face. And I believe this is also used in telephony R&R calculations. Maybe one of the most difficult and tricky ear simulators to work with and understand is the IC711 simulator. The 711 is tricky because it's meant to capture the entire ear canal, but a lot of devices go into the ear canal a certain distance. The ear canal is generally assumed to be roughly 7 millimeters in diameter on average, and has a length between about 2.5 and 3.5 centimeters long. And the 711 is trying to capture that entire canal, but when you put a device into that, you're driving a smaller volume than what the 711 is actually trying to represent. So there is a little trick you can do in Ares to try to compensate for that. And I'm going to show you that in this demo. So here's Ares again. I'm going to create a new modeler module, and I'm going to go back to my pressure, and I'm going to go to create an ear simulator. I'm going to set that simulator to the 711. I'm going to go ahead and I'm going to drive it, create a graph element, and I'm going to look at let's solve this. I'm going to look at the impedance into it. Here's the graph element window that was created. I'm going to set the line weight to 3. Make it nice and thick. Set it for all. And that didn't work. What did I do wrong? Line weight 3. Set all. Okay. There we go. So here's the impedance into that simulator. It had the highest impedance of all the simulators we looked at because it has a very small sealed volume, which creates this huge impedance at low frequencies. Now, what you can do in Ares, it's a little trick. I'm going to create a circular port. And actually, before I do that, what do I want to do? I want to, just mostly for educational purposes, I want to figure out what is the equivalent volume of that of this ear simulator. How many cc's is that simulator simulating? I'm going to go ahead and plot real and imaginary for this as well. And here's its real and imaginary impedance. You can see that its impedance is dominated at low frequencies by a sealed condition. 1/j omega here, that's a sealed volume impedance. It's inductive at high frequencies, and here's our resonance. But how big is this volume? You can do that by creating a volume element. We're going to need to drive it with something. I'm going to type 711 impedance, the impedance for the 711 into buffer A. I'm going to go down here and hit calculate and bring up the graph. So the default volume impedance is shown in blue. It's the current buffer. It's quite a bit smaller than the volume that's used in the 711, but it's not smaller by, or the impedance is smaller, which means the volume is larger, but it's not larger by a factor of 10. It's maybe larger by a factor of maybe 2.5 or so. So let's go to this volume, and I'm going to instruct Ares to compute the height, and I'm going to specify the volume. So instead of almost 4 cc's, I'm going to change it to 3 cc's. Hit calculate and go back here. Didn't update it correctly. We should be a little closer. So we're a little closer with 3 cc's, but apparently that's still too big. I'm going to change it to 2. Hit calculate. A little closer. 1.5. Calculate. So I'm just going to pause this and adjust the volume till it's dead on. Okay, it seems that a volume of about 1.25 cc's is the best fit here. The sealed volume isn't matching the simulator perfectly because that simulator does have some other components to it, but it's pretty darn close. So you can see that the impedance is matching pretty good at low frequencies. So that simulator is simulating about 1.25 cc's. Now I did this for a diameter of 10. I'm going to change that to a diameter of 7, which is more representative of an ear canal, and that would have the height or the length of 32.48 millimeters. So I'm going to go ahead and copy that, and I'm going to paste that into the length of this simulator. I'm going to get a diameter of 7. And now the volume of this port is roughly equal to the volume inside of this ear simulator. And I'm going to go ahead and connect that up. And I'm going to do something a little tricky. Instead of having the length being positive, I'm going to have the length be negative. Mathematically, what that'll do is it'll suck that impedance out of the ear simulator. It'll like create a an ear canal that's a negative 32 millimeters long, and it'll propagate the sound down into the ear simulator 32 centimeters. So I'm going to hit calculate. I'm going to connect this back up to our ear simulator and see what the graph is showing. Okay, I actually need to connect that to the front of this tube. So we're interested in the combination of this impedance that we've sucked out and the ear canal together. So let's try that. Okay. So the blue is the impedance into the port, which is sucking air out of the ear simulator. And notice that the impedance went up quite a bit, particularly at low frequencies. And it went up here by about 25 dB. So the impedance now is larger by a factor of 10, which is pretty big. We could probably play around with the length a little bit more and get it to maximize the impedance a little better. But I'm not going to bother doing that. The impedance still has this dip at the higher frequencies due to resonance. That'll shift around as we change this port length. But we can change this port length to simulate how far an ear insert device is going into the canal. So we know that this simulator is roughly simulating an ear canal that's 7 millimeters in diameter and 32.5 millimeters long. Let's say our device goes into the ear canal about 10 millimeters. So I'm going to set this to a length of 10 millimeters. To do that, I'm going to multiply that by 0. It's just a handy trick that allows me to make a change to the parameter and not lose the original value. And then I'm going to subtract another 10 millimeters. So let me call this negative 32.48 millimeters impedance. And I'll hit calculate, go back to the graph, and I'm going to get rid of this imaginary stuff going on down there. It is important to understand what's going on, but we'll just look at the magnitude for this. So here we've sucked out almost all the volume in red. In blue, we've sucked out only 10 millimeters. And it's shifted this resonance, it's flattened it out. So this is the impedance we're seeing when we insert the device 10 millimeters into the ear canal. And this is a useful feature to keep in mind and a useful trick to try to use. I probably should have incorporated it into the ear simulator itself. I just haven't done that. And it would only be really applicable to the 711. Now the effect of this on the response is important. I'm going to create another graph element, hook it up to the diffuse field point. Here's the graph. I'm going to set the line buffer to 3 again. Normally a weight of 1 is good if you're working on the computer, but for these videos I want a thicker line to make it more visible. So I'm going to copy this in the buffer A. I'll say it's with a negative 10 with a 10 millimeter insert. And now I'm going to recompute this without that 10 millimeter insert. I'm going to disconnect it completely, rerun this, and now here's our diffuse field response in green with that insert. Without that insert, we're getting the blue curve. So this is what you would predict without being able to insert the device farther into the ear canal. But in reality, what you should expect is the green curve if your insert device did go 10 millimeters into the ear canal. And so you can use this trick to simulate that effect with Ares and the ear simulators. There was an error in the IEC 711 or Type 2 ear simulator. This is related to the ERP to DRP correction curve for that simulator. The release of Ares in late 2016, which would be 1.40 or higher, addresses this problem. The problem arose from looking at the sensitivity curve for the ear simulator out of the B&K datasheet. The B&K 4157 is the equivalent version of the 711 for B&K, and the datasheet publishes a typical sensitivity curve, which is shown in green here. All the other sensitivity curves found in B&K's literature are correct, but this one isn't. I have no clue where they got that sensitivity curve. The correct curve, the correct ERP to DRP sensitivity curve is shown in blue, and they're substantially different. The original curve that was used in Ares misses this resonance at 5 kilohertz completely, which is going to cause some significant error in its simulation results. The correct curve doesn't come from any published data that I've been able to find, any published curve. It comes from the equivalent circuit model for the 711 as presented in the B&K 4195 datasheet. Basically, this blue curve is the transfer function from the input to the voltage across this final capacitor here, which I believe is representing the microphone's diaphragm, capacitive diaphragm. But the blue curve is the correct curve, and that's been made in versions of Ares 1.4 and higher. I apologize for any problems that this has caused. If you're aware of any other issues like this that aren't making sense, please contact us, and I'll be happy to look into it and try to address what the issues may be. I also wanted to show how you can kind of create your own ear simulator. Again, the ear simulator is mostly composed of the impedance loading function and the ERP to DRP correction curve. Now, Macintosh Applied Engineering sells a device called a SEMA that can measure the surface impedance into various structures. And here I've used the smaller SEMA device to measure the impedance into the ear canal of our hat's ear. So this would be for a particular coupling of a device into the hat's ear, or you could put this up to a human ear or some other acoustic device that you're trying to drive and measure its impedance. Once you get its impedance, we can use that in the Ares simulator to simulate its effect on an acoustical circuit. You can also measure the ERP to DRP correction curve yourself by placing a microphone in front of your hats, or you can just use a built-in curve. So I'm actually going to use the built-in curve for a hat's, but I'm going to use this impedance. To do that, I'm going to go back to Ares, and I'll create a new modeler module. I'm going to create a pressure source, and I'm going to need this ear simulator in a moment. I'm going to create a resistance, and I'm going to import the impedance that we just saw into this resistance, but it's going to be imported as a series impedance. To get that absolute impedance, I need to put a pressure release on the other side, and then for the ERP to DRP correction, I'm going to need an acoustical transfer function element. I'll hook that up to the front. This is going to be our ERP point. I'm going to hook up that simulator just so that we drive it, and I'm going to select, I'll cover this in a bit, I'm going to select the 4128 ear simulator, and I'm going to hit calculate. Let me set this pressure to 0. I'll hit calculate, And we'll create a graph element, hook that up to the DRP. So here's our graph element. Here's our ERP to DRP correction for that hats. Let me set the line weight a little heavier again. And now I want to copy this and put it into that transfer function element. So I'm going to right click on this, tell it to copy this trace data out. This copies it in a space delimited file format. I can show you that real quick by running Notepad and just pasting the data in. So this is the text data that was just copied out of that graph by right clicking on it. I can paste that data into this resistance element by I'm sorry, I'm dealing with the transfer function right now. I can paste that data into the transfer function element by saying paste from clipboard. It's 2 columns and I don't want to invert it. So I'm going to hit OK. So now I've got this ERP to DRP correction curve in this transfer function element. I want to import the impedance data that I measured with the SEMA device into this element. To do that, I'm going to hit load from data file. I've navigated to the directory where I exported that data out from the surface impedance module. To use it, I've got to say, let's go ahead and use it. And I now should be able to hit calculate. And if I create another graph element, I'm going to change this to impedance. Let me, I want to call this impedance into the 4128 at 2 newtons. Now let's change that. Let's do I'm going to go ahead and do the 711, I guess. Hit recalculate. So I'm going to call this the 711 impedance. Copy that in the buffer A. Here's the graph that was created showing the impedance. Let's do the line weight again. So here's the 711 impedance. Now I'm going to come down here, and if I did everything right, I'm going to look at the impedance into their simulator using the SEMA data that I measured. So the blue curve is the SEMA data that I measured. It's certainly not looking like the 711. There's a huge leak at low frequencies. Let's call this the SEMA data. Copy that in the buffer B, and let's go back up here. And now let's choose the high leak simulator, hit calculate. So the 711 is in green, the SEMA data is in red, and the high leak is in blue. Notice that the SEMA data is best matching the high leak at low frequencies, but we do get some different resonance behavior. I'm sorry, it's matching it at low frequencies, but it's not matching it at high frequencies due to different resonance behavior because we're interacting with that rubber pinna in a different way. So the shape, structure, size of how your device interacts with a human ear or an artificial pinna ear affects its impedance quite a bit, and you will get a different different behavior than what any of these standard ear simulators provide. So there may be a reason for you to want to use the May tools to develop the impedance and transfer functions that relate to your particular device rather than trying to get it to match one of these existing simulators. So I didn't plot it, but we can come down here and plot the pressure here. Let's bring that graph up to the top. And it's it's the same transfer function that we saw with the 4128 simulator up here. So that brings me to let me see what the next topic is. To the 4128 simulator. So when you bring up the simulator options, you do see the option for the 4128C, which is the B&K head and torso simulator on their hats. This ear right here is the 4128C. At one time, I did take a different SEMA device and measure the impedance into this for various pressures onto the rubber pinna. Now the device that I used had a diameter of 50 millimeters, so it was rather large, and I wanted to create a series of impedances that would be representative of a large phone being pressed into the B&K rubber pinna, and that's where these options come from in the SEMA device. These aren't standard impedances; they're impedances that I measured and used in my work. For these simulators, the ERP to DRP transfer function that was used came from table 14A out of the P.58 specification. That's essentially the transfer function you get if you do this type of a measurement here, where you just put a microphone in front of the B&K hats. The DRP to diffuse field transfer function that was used came out of the IEEE standard shown here, which is the same transfer function used throughout all of the ear simulators in Ares. So we're almost done. I made up these slides, and as I was going through the presentation, I realized I forgot one old common ear simulator that's used particularly in the hearing aid industry, and that is the 2cc coupler. We found that the IC711 simulator is capturing about 1¼ cc's of air volume. Well, a while ago, it was believed that the common volume inside of a typical ear was around 2 cc's, and so a 2cc coupler was developed, and this is just a simple sealed volume. It doesn't contain any of the high frequency resonances created by the eardrum, by the fluid on the other side of the eardrum, by the cochlea and the rest of the inner structure. It's just meant to capture the air in the ear canal itself. And to simulate that, you don't need the ear simulator. You just need a simple volume element, and you set its volume to be 2 cc's, and that captures the behavior of the 2cc coupler. So that's why you won't see that in the ear simulator. There was just no need for it. So that wraps up my presentation on ear simulators. I hope you found it useful. I know it was long and a bit tedious, but hopefully the information I presented is 100% accurate. If you notice some discrepancies or if you have some other comments, please feel free to contact us and let us know what you think. Thank you for your time, and I hope you find these tools useful.